Okay, we have VSEPR theory, valence shell electron pair repulsion theory. And it says determine the electron pair arrangement, the molecular geometry, the bond angles, and polarity of each of the following species. I'm going to start with this. I forgot to put these ones in. That kind of follows a nice pattern if we do it this way. So what you do first is write the Lewis structures of each of these. Now we've done that in the previous chapter, so I'm going to assume you know how to do that. Here's the Lewis structure for beryllium difluoride. Then they want to know the electron pair arrangement. So we look at the central atom. It has two pairs of electrons around it. They're going to be as far apart from each other as possible, so this is going to be 180 degrees. And that means that these atoms are in a straight line. So the electron pair arrangement is going to be linear. Then they want to know the molecular geometry or the molecular shape. So write molecular geometry. And the electron pair arrangement is just these electrons, whether they're a lone pair or they're bonding. But the molecular geometry depends on the nuclei. These three nuclei are right in a row. So in this case, the electron pair arrangement and the molecular geometry are the same. And that's going to be the case when there are no lone pairs on the central atom. They want to know the bond angle. I gave you that. When you have two pairs of electrons or two groups of electrons on the central atom and no others, then they're going to be 180 degrees from each other. What about the polarity? Well, you have beryllium, you have fluorine, and the electron density, the fluorines are very electronegative, so they pull the electron density towards them. But since they're straight across from each other, this fluorine pulling on the electron density cancels this one, so the electron density stays put, so this thing would be nonpolar. And that's what I'll be looking for each of these. So that's what we will want to do, is find the electron pair arrangement, the molecular geometry, the bond angle, or bond angles if there's more than one type, and then the polarity. These are nonpolar. Let's look at boron trifluoride. Write out the Lewis structure. Again, if you have to pause and do this out, it takes you a little time, that's fine. But if you are lost at this point and say, well, what are you doing here? You got to go back to chapter 9. That's where I covered this really in depth. So now we look at the central atom. It has three bonding pairs. So it has three bonding pairs of electrons, and they're going to try to be as far from each other as possible. In this case, they're 120 degrees from each other. So the electron pair arrangement is what we call trigonal planar. These lone pairs these bonding pairs are 120 degrees from each other in the plane of the paper, so they're trigonal planar. Then the molecular geometry. Now we look at the nuclei. All four nuclei are in the plane. The outer nuclei are 120 degrees from each other, so this is also trigonal planar. So, and that's because we have no lone pairs on the central atom. The bond angles, they're all 120 degrees. And then this, again, this is a little tougher to see, but each fluorine is pulling on the electron density from the boron because they're so highly electronegative, but all three are pulling in opposing directions. They're none of them are pulling directly across from a fluorine, but if you picture it as, let's say this was a tire, and each of these bonds were ropes, and at the end were three people equally strong pulling in 120 degrees from each other, that tire wouldn't move. There would be no movement of that center. Same with the electron density. Each fluorine is trying to pull on this electron density. It stays put, so this is nonpolar. Okay, so I'm going quickly, but you can always rewind. You can always look at it. I just want to make sure that I can cover a huge number of these in the same video. So let's look at methane. Now the Lewis structure is this. But there are four bonds, and so we can draw it as if it were planar, but when we want to draw the molecular geometry, we have to draw it in the 3 dimensions it's actually in. The bonds, there's 4 bonds, so electron pair arrangement, they're all going to be 109.5 degrees from each other. Here they'd only be 90 degrees from each other. So how we do this, or how we think of it, is these 3 atoms are in the plane of the paper. Now if this hydrogen were to twist up, and this one were to twist back, so this guy came closer to us, this went further away, it would become a 3-dimensional structure just like this, and we can actually, that we show it by this wedge, meaning this hydrogen is coming out of the paper. This dash line indicates the hydrogen is deeper inside of the table, and then these guys are in the plane of the paper. So we do our best to draw it 3-dimensionally, and that is called, the electron pair arrangement is called tetrahedral. The molecular geometry, since there are no lone pairs on the central atom, is going to be the same. If we looked at just the electron pair, we're just looking at the electron pairs. We don't care about the outer atoms, but when we take into account the nuclei, we find that they're in a tetrahedral position. The bond angle for this is 109.5 degrees. This is something you just have to memorize. You have to know that if it's tetrahedral, it's 109.5 degrees. And then the polarity, well, the hydrogens are all pulling in opposing directions, so this is nonpolar again. Don't worry, we'll get to some ones that are different mode. These are the very simplest ones. Now ammonia, if you write out the Lewis structure, we get this. But notice there are 4 pairs of electrons around the nitrogen. So if we drew it a lone pair, then we have the hydrogen, this hydrogen, and it looks very similar to what we have up here. The electron pairs, if we just think of them as 4 electron pairs, they're all going to be 109.5 degrees from each other. We'll have to make a little correction there in a second, but the electron pair arrangement, even though it has fewer atoms, the electron pair arrangement is the same. It's tetrahedral. The molecular geometry, though, to be tetrahedral, you need to have an atom at each vertex. Here we're missing one, so it becomes kind of a squat pyramid. And we call this one the Trigonal Pyramidal. So make sure, sometimes I call it just a trigonal pyramid. Trigonal planar, tetrahedral, trigonal pyramidal, yep. And then, or pyramidal, either way. Now the bond angle, because this lone pair is diffuse, it's not directed to an atom, it spreads out a little bit, pressing down on the bond angle. Now the bond angles are only between atoms, so there's no real angle between this lone pair and this bond. So we just look at these, and the, let me rewrite it here. So you have this lone pair that spreads out, and the bond angle here is going to be slightly less than 109.5 degrees because of the diffusion of this lone pair. So that's something you have to have in there. It's going to be less than 109.5 degrees. How much less? It depends on the molecule. If you had fluorines here, or if we had chlorines, it would be different than hydrogens, but they'd always be less than 109.5 degrees. And because of that, since there's no hydrogen up here, there's only a flow of electrons in the general direction towards nitrogen, and there's nothing pushing back on it. This would be a polar molecule, the first one that we've had. So there's no balancing of the flow of electrons, because there's nothing above here pushing back down. Where is it? Yeah, pushing back down here. So it's going to be our first polar molecule. All right, now we have, if I have to break this up into 2 lectures, I will, but for water, here's our Lewis structure. So it's good to draw this first so that we can see that we have 4 pairs of electrons. So the electron pair arrangement is going to be tetrahedral. Again, I'm just going to write tetra. So oxygen, we have a lone pair here, then we have the hydrogen. But you can see it still has that tetrahedral shape for the electron pairs. But for the molecular geometry, we have to just go with the atoms. We don't worry about the electron pairs with the molecular geometry, because the molecular geometry is based off of the big masses of the nuclei, so this is going to be bent. And when I draw the Lewis structure of water, I almost always draw it bent because I know that that's what it is, but you can certainly draw it like this. But once you put it into its structure, you know, the true structure, you have to show that it's bent or angular. The bond angle, there's only one bond angle now. So I'll draw it this way. We'll put the hydrogens, since all the positions are equivalent, put the lone pairs here. These are pushing down on these angles, so instead of being 109, they're less than 109 degrees. I think water is 104 point something, so it's not, you know, you can see it's not a lot, but it is definitely different than 109.5. So it's going to be less than that for the only bond angle we have in this one. And definitely polar, because the oxygen steals electron density from the hydrogens, and there's nothing countering it. So you have to look at the symmetry of the molecule. Is there would those the electronegative characteristics of the atoms, would they counter each other and stop each other in their tracks, or is there an imbalance here? There's nothing pulling back. So for now, let's move on to higher level here, or the more bonds. So we have phosphorus pentafluoride, and it has 5 bonds to it. Now these bonds are going to try to get as far from each other as possible, so this is the first time we've seen this one, and this is a little trickier than what we've had before. We have 3 fluorines, or 3 bonds that are in a plane, and then we have one above and one below. These ones on the outside are called axial. And then the ones that you can picture it kind of like an axis of a globe, and then these guys are around what we call the equator, or these are called equatorial bonds, or if these are fluorine, you know, since they're fluorines, they're equatorial fluorines. The bond angle between is 90 degrees here, and it's 120 degrees here. So this is the first molecule that has 2 different bond angles, so we have to keep that in mind. The electron pair arrangement is what we call trigonal bipyramidal, or bipyramidal, because there is trigonal base, and you can see that here's one pyramid, and then there's one below. If we looked at the, you know, we connect all the atoms with lines, we can see it's like 2 trigonal-based pyramids stuck together. The molecular geometry, or the shape, is going to be the same thing, so we'll just call it trigonal tri-bip. The bond angles are 90 and 120 degrees exactly, because there's no lone pair crushing down in any way. And then it's nonpolar, because these fluorines cancel each other, and then these ones cancel each other. So these ones cancel like they did in the beryllium difluoride. These ones cancel like they did in the boron trifluoride. So this is nonpolar. Okay. For this one, we end up with this Lewis structure. But we can see that we have 5 pairs of electrons. So from here you could say that the electron arrangement is trigonal bipyramidal, but let's draw it out to see. We have this fluorine, then we have a fluorine here, here, and then the lone pair, it seems like it could go either equatorial or axial, but it always goes equatorial. And if we had 2 lone pairs, they both go equatorial, and if we had 3, they'd all go around the equator, because there's more room for it to spread out. So you have to be careful, make sure, don't put the lone pair up on the axial, though sometimes it looks better to do that. We can't do that here. So the electron pair arrangement is trigonal bipyramidal. I'm going to abbreviate it again. Now the molecular geometry, though, since there's a lone pair, there's going to be a different geometry. And what we call it, you see that this is, let me turn it this way, this is like the board, oops, right, the board of a seesaw, and these are like the legs. So what we call this is the seesaw shape. So it's nice to be able to use a term like seesaw when you're talking about real science. And for some, they don't like that name, so they call it a distorted tetrahedron. I like to have a little sense of humor about these things, so Seesaw is good. But the more stoic of the scientists like it to be called distorted tetrahedron, or tetrahedral. Now, the bond angle should be 90 here, but because of the lone pair spreading out, it's less than 90, and this is less than 120. So our bond angles would be, and you got to put that less than in there. You're going to get a point or so off, because it isn't 90 degrees. It isn't exactly 120 degrees. It's slightly less, unless all of the electron pairs are bonding pairs, then they are exactly 90 and 120. Is there a polarity? Yes, because these fluorines might cancel each other. They're actually slightly lowered, so they don't quite cancel, but these fluorines don't have anything to cancel them, so this is polar. SF6, you draw this out. This is one of the ones, we're into the exceptions to the octet rule. Octahedral, so the electron pair arrangement is going to be what we would call octahedral. So this is a name that you just need to know. See, there's a square base here, but if you connect all of the fluorines, you get an 8-sided object. It's like an 8-sided dice if you played Dungeons and Dragons or those D20 games. But it's an 8-sided object, so that's where octahedral comes from. Since there's no lone pairs, the molecular geometry is going to be the same. This is octahedral. And there's only one bond angle at 90. Well, from here to here is 180, but we're generally concerned with the ones that are right next to each other. So this is 90 degrees, and that's all you need to put there. You don't have to put 180. And is it polar? Nope, all the fluorines cancel each other. They're directly across from each other, so this is nonpolar. And let's see, we got four more. I'm going to stop here so that I feel a little bit rushed. So we'll do the last 4 in the next video.